The guidelines for installing cable tray cable, specifically a 3-phase 4-wire 277/480 volt system in metallic conduit, are as follows. Firstly, electrical code compliance is paramount. Adhere strictly to the requirements outlined in the National Electrical Code, commonly referred to as the NEC, as well as any local building codes and the manufacturer's specifications for the cable and conduit being used. Secondly, conduit selection is critical. For environments that are either wet or corrosive, opt for Schedule 80 polyvinyl chloride conduit. This type of conduit offers superior resistance to moisture and chemical degradation. In contrast, for dry environments, galvanized steel conduit is typically suitable, providing adequate mechanical protection and corrosion resistance. Regardless of the material chosen, ensure that the conduit diameter is sufficiently large to accommodate the cable bundle that will be installed within it. A minimum fill capacity of 20% should be maintained to facilitate heat dissipation and prevent damage to the cables during installation and operation. Thirdly, cable selection is of utmost importance. Select a cable that is specifically rated for the voltage and current requirements of the circuit. In this case, a 4-wire 277/480 volt cable must be rated for the desired ampacity to safely handle the expected load. Typically, type THWN or THHN copper conductors are used, as these provide excellent conductivity and are insulated with materials suitable for the anticipated temperature and environmental conditions. Fourthly, the conduit installation process must be carried out meticulously. Securely install the conduit to the cable tray using appropriate conduit clamps or brackets designed for this purpose. Maintain a minimum clearance of 6 inches between the conduits and the sides of the cable tray to ensure adequate ventilation and accessibility. Additionally, provide support for the conduit at regular intervals, ideally every 5 feet, to prevent sagging and ensure structural integrity. Fifthly, cable installation requires careful attention to detail. When pulling the cable into the conduit, ensure that it is free from any twists, kinks, or damage, as these can compromise its performance and lifespan. Leave approximately 12 inches of slack at each end of the conduit to facilitate connection to equipment and allow for future maintenance. Secure the cable to the conduit using cable clamps or supports every 3 feet to prevent movement and strain on the connections. Sixthly, making proper connections is crucial for the safe and reliable operation of the system. Terminate the cable strictly according to the manufacturer's specifications, using appropriate connectors and sealing compounds, particularly in wet or corrosive environments, to prevent moisture ingress and corrosion. Seventhly, grounding and bonding are essential safety measures. Ground the conduits using grounding clamps or bushings to provide a path for fault currents to return to the source, thereby minimizing the risk of electric shock. Bond the conduit runs using flexible bonding jumpers at each splice and termination point to ensure electrical continuity throughout the system. Eighthly, proper labeling is important for future identification and maintenance. Clearly label both ends of the conduit with a circuit identification and voltage to facilitate troubleshooting and prevent accidental contact with energized circuits. Ninthly, rigorous testing is necessary to verify the integrity of the installation. Perform insulation resistance testing using a megometer, as well as continuity and ground fault testing, to ensure that the insulation is free from faults and meets all applicable safety standards. Tenthly, protection of the installed conduit is essential for long-term reliability. Protect the conduit from physical damage during and after installation by using appropriate covers or guards. Use conduit sealants or other measures to prevent moisture ingress, which can lead to corrosion and premature failure. In addition to these 10 guidelines, there are several additional considerations to keep in mind. Firstly, consider using cable tray brackets that are specifically designed for supporting conduit, as these can simplify installation and provide a secure and stable mounting platform. Secondly, allow for expansion and contraction of the conduit due to temperature variations by using expansion couplings at appropriate intervals, especially in long conduit runs. Thirdly, in areas that are prone to earthquakes, use seismic restraints to prevent the conduit from shifting or falling during seismic events. Finally, it is essential to inspect and maintain the installation regularly to ensure its ongoing safety and integrity. Check for any signs of damage, corrosion, or loose connections, and address any issues promptly to prevent potential hazards. By adhering to these guidelines and considerations, ensure a safe and reliable installation of cable tray, cable, and metallic conduit. The NEC provides comprehensive guidance on electrical installations, and staying up to date with the latest revisions is critical for compliance and safety. Article 392 covers cable trays, and Article 300 covers general wiring methods. Article 314 addresses junction boxes and pull boxes, which may be needed at conduit terminations. Cable selection should comply with Article 310, which provides tables for allowable capacities of insulated conductors. Grounding and bonding requirements are detailed in Article 250. Conduit fill calculations are covered in Chapter 9, Table 1 and associated notes. The requirements for conductor installation are specified in NEC 300.4, which addresses protection against physical damage. The NEC also specifies the proper use of fittings and connectors in 314. The selection of conductors must be based on the application, load requirements, and environmental conditions. The ampacity of conductors should be determined per NEC Table 310.15b16 for conductors rated 600 volts or less, and should be adjusted according to 310.15c for ambient temperature and the number of conductors in a raceway or cable. The insulation type, such as THHN or THWN, must be suitable for the operating temperature and environment. Cables and cable trays must be installed in accordance with NEC 392.8, which requires that cables be supported and secured to the cable tray. When installing cables and conduit, the conduit must be sized according to Chapter 9, Table 4 and Table 5a. The number of conductors permitted in conduit is also dictated by these tables. For example, using Table 4, one would determine the maximum number of conductors allowed based on the conductor size and conduit type. For grounding and bonding, all metallic conduit systems must be grounded in accordance with NEC 250.45 and 250.92. Grounding ensures a low impedance path for fault current. Bonding reduces the potential for voltage differences between metallic parts. Grounding electrodes must meet the requirements of NEC 250.50, which includes items such as metal underground water pipes, grounding rings, and rod and pipe electrodes. Proper labeling of electrical circuits and equipment is essential for safety and maintenance. NEC requires that all circuits be clearly identified per 110.22, using labels that are durable and easily readable. The labels should indicate the circuit's purpose or function. Testing is a critical part of the installation process to ensure that the electrical system is safe and functioning correctly. Insulation resistance testing, or Megger testing, is used to verify the integrity of the conductor insulation. The test is performed by applying a high voltage direct current and measuring the leakage current. A high resistance reading indicates good insulation. Continuity testing confirms that there are no breaks in the conductor. A low resistance reading indicates good continuity. Ground fault testing verifies that the grounding system is functioning correctly. The test is performed by injecting a fault current into the grounding system and measuring the voltage drop. A low voltage drop indicates a good grounding system. Protection from physical damage is important to maintain the integrity of the conduit and cables. The NEC requires that wiring methods be protected from physical damage per 300.4. This can be achieved by using rigid conduit, metal-clad cable, or by installing wiring in protected locations. Moisture ingress can cause corrosion and damage to electrical equipment. The NEC requires that enclosures be suitable for the environment per 314.15. This may involve using weatherproof enclosures, sealing fittings, or other methods to prevent moisture from entering the enclosure. Expansion and contraction of conduit can occur due to temperature changes. The NEC recommends using expansion fittings to accommodate this movement per 300.7b. Seismic restraints are necessary in areas prone to earthquakes to prevent the conduit from shifting or falling. The NEC recommends using seismic restraints per 300.11a. Regular inspections and maintenance are essential for ensuring the long-term safety and reliability of the electrical system. The NEC recommends that electrical systems be inspected and maintained per 110.3b. This includes checking for loose connections, damaged wiring, and corrosion. Proper maintenance can prevent electrical hazards and extend the life of the electrical system. The National Electrical Code provides specific guidelines for the installation of electrical systems, including cable trays and conduits. These guidelines are intended to ensure the safety and reliability of the electrical system. The NEC is updated every 3 years, so it is important to stay up to date with the latest revisions. In addition to the NEC, local building codes may also have specific requirements for electrical installations. It is important to check with the local building department to determine what codes are in effect. The manufacturer's specifications for the cable and conduit should also be followed. These specifications provide information on the proper installation and use of the equipment. Failure to follow these specifications can void the warranty and may create a safety hazard. Electrical work should only be performed by qualified electricians who are familiar with the NEC and local building codes. Unqualified individuals should not attempt to perform electrical work, as this can be dangerous and may violate the law. The information provided is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician before performing any electrical work. The installation of cable tray cable and metallic conduit, especially within a 3-phase 4-wire 277/480 volt system, demands meticulous adherence to safety protocols and established standards. Firstly, code compliance is not merely a suggestion but a mandatory prerequisite. The National Electrical Code, more commonly known as the NEC, serves as the bedrock of safe electrical practices in the United States. This document is regularly updated to reflect the latest technological advancements, safety concerns, and best practices in the electrical industry. Local building codes, which may be more stringent than the NEC in certain aspects, also play a vital role and must be observed. Furthermore, the manufacturer's specifications for the cable, conduit, and associated hardware provide critical guidance on proper installation techniques, limitations, and potential hazards. Neglecting any of these regulatory or informational sources can lead to non-compliance, increased risk of electrical hazards, and potential equipment failures. Secondly, the selection of conduit material is heavily dependent on the environmental conditions in which the system will operate. Schedule 80 polyvinyl chloride, known as Schedule 80 polyvinyl chloride, conduit is often chosen for locations prone to moisture or corrosive substances. The thicker walls of Schedule 80 polyvinyl chloride conduit provide enhanced resistance to physical damage and chemical attack, thereby prolonging its lifespan in harsh environments. Conversely, galvanized steel conduit is typically preferred for dry, indoor applications due to its robust mechanical strength and inherent resistance to corrosion in non-aggressive settings. The diameter of the conduit must also be carefully calculated to ensure adequate space for the cable bundle. A minimum fill capacity of 20% is recommended to facilitate effective heat dissipation and to prevent undue stress on the cables during installation and thermocycling. Overfilling the conduit can lead to overheating, insulation breakdown, and ultimately, electrical failures. Thirdly, cable selection is a critical engineering decision that directly impacts the performance and safety of the electrical system. Chosen cable must be rated to withstand the maximum voltage and current demands of the circuit. In a 4-wire 277/480 volt system, the cable must be specifically designed and certified for this voltage level. Type THWN or THHN copper conductors are commonly employed due to their excellent conductivity, thermal stability, and resistance to moisture and abrasion. The ampacity rating of the cable, which dictates its ability to safely carry electrical current, must be carefully matched to the expected load to prevent overheating and potential fire hazards. Fourthly, the installation of the conduit requires precision and attention to detail. The conduit must be securely attached to the cable tray using appropriate clamps or brackets that are specifically designed for this purpose. Maintaining a minimum clearance of 6 inches between the conduits and the cable tray sides promotes adequate ventilation, facilitates future maintenance, and reduces the risk of accidental contact. Proper support for the conduit must be provided at regular intervals, typically every 5 feet, to prevent sagging, minimize stress on the connections, and maintain the structural integrity of the system. Fifthly, the process of pulling the cable into the conduit demands careful handling and meticulous execution. The cable must be free from any twists, kinks, or physical damage, as these imperfections can compromise its electrical performance and reduce its lifespan. A lubricant specifically designed for cable pulling can be used to minimize friction and prevent insulation damage during installation. Leaving approximately 12 inches of slack at each end of the conduit provides sufficient length for making connections to equipment and allows for future adjustments or repairs. Securing the cable to the conduit using appropriate clamps or supports every 3 feet prevents movement and reduces strain on the connections. Sixthly, making reliable and secure connections is paramount to ensuring the safe and efficient operation of the electrical system. Terminating the cables according to the manufacturer's specifications is essential to maintain the integrity of the connections and prevent premature failures. The use of appropriate connectors and sealing compounds, particularly in wet or corrosive environments, is critical to prevent moisture ingress and corrosion, which can lead to electrical faults and equipment damage. Seventhly, grounding and bonding are fundamental safety measures that protect against electrical shock and minimize the risk of equipment damage. Grounding the conduits using grounding clamps or bushings provides a low impedance path for fault currents to return to the source, thereby tripping circuit breakers or fuses and preventing prolonged exposure to dangerous voltage levels. Bonding the conduit runs using flexible bonding jumpers at each splice and termination point ensures electrical continuity throughout the system, minimizing the potential for voltage differences between metallic parts and further reducing the risk of electric shock. Eighthly, clear and comprehensive labeling is essential for facilitating future maintenance, troubleshooting, and ensuring the safety of personnel working on the electrical system. Labeling both ends of the conduit with the circuit identification and voltage provides critical information for identifying the circuit's purpose, preventing accidental contact with energized conductors, and minimizing the risk of electrical hazards. Ninthly, thorough testing is necessary to verify the integrity and safety of the electrical installation. Performing insulation resistance testing using a megometer, commonly known as a megger, assesses the condition of the conductor insulation and detects any potential weaknesses or damage. Continuity testing confirms that the conductors are properly connected and that there are no breaks or open circuits. Ground fault testing verifies that the grounding system is functioning correctly and that it can effectively clear fault currents to protect against electrical shock and equipment damage. Tenthly, protecting the installed conduit from physical damage is critical to ensuring the long-term reliability and safety of the electrical system. Using appropriate covers or guards to shield the conduit from impacts, abrasion, and other potential hazards can prevent damage that could compromise its structural integrity and electrical performance. Applying conduit sealants or other measures to prevent moisture ingress is essential in wet or corrosive environments, as moisture can accelerate corrosion and lead to premature failures. In addition to these 10 core guidelines, several additional considerations can further enhance the safety and reliability of the installation. Utilizing cable tray brackets specifically designed for supporting conduits simplifies the installation process and provides a secure and stable mounting platform. Allowing for expansion and contraction of the conduit by incorporating expansion couplings at appropriate intervals is particularly important in long conduit runs, as temperature fluctuations can cause significant movement that could stress the conduit and connections. In areas prone to seismic activity, employing seismic restraints to secure the conduit and prevent it from shifting or falling during earthquakes is essential for maintaining the integrity of the electrical system and preventing potential hazards. Implementing a regular inspection and maintenance program is crucial for identifying and addressing any potential problems before they escalate into major issues. Checking for loose connections, damaged wiring, corrosion, and other signs of wear and tear allows for proactive maintenance that can extend the lifespan of the electrical system and ensure its continued safety and reliability. Electrical systems operating at 277/480 volts pose significant hazards, and only qualified and experienced electricians should perform installations, maintenance, and repairs. Working with high-voltage electricity requires specialized knowledge, skills, and equipment to minimize the risk of electrical shock, arc flash, and other potential hazards. Regular training and continuing education are essential for electricians to stay up to date on the latest safety standards, best practices, and technological advancements in the electrical industry. Following these guidelines and considerations is essential for ensuring the safe and reliable installation of cable tray cable in metallic conduit, particularly within a three-phase, 4-wire, 277/480 volt system. Prioritizing safety, adhering to industry standards, and employing qualified personnel are key to minimizing the risk of electrical hazards and maximizing the performance and longevity of the electrical system. The NEC is revised and updated on a 3-year cycle. It is essential to ensure that the electrical installation complies with the latest edition of the NEC. Various articles in the NEC pertain to cable trays, conduit, and conductors. Article 392 specifically addresses cable trays, covering aspects such as installation, support, and allowable fill. Article 300 provides general wiring methods, including requirements for protecting conductors and ensuring proper connections. Article 314 covers junction boxes, pull boxes, and handhole enclosures, which are commonly used in conduit systems to provide access for wiring and connections. Article 310 details the requirements for conductors for general wiring, including ampacity, insulation, and identification. Article 250 focuses on grounding and bonding, providing essential information for ensuring electrical safety and minimizing the risk of shock. Chapter 9 includes tables and examples for calculating conduit fill, conductor properties, and other essential parameters. The ampacity of conductors must be determined in accordance with NEC Table 310.15b16, which provides allowable ampacities for conductors rated 0 to 2000 volts based on insulation type and temperature rating. Adjustments to ampacity may be required based on ambient temperature and the number of conductors in a raceway, as outlined in NEC 310.15c. The equipment grounding conductor (EGC) must be sized in accordance with NEC 250.122, which provides minimum sizes for EGC based on the rating of the overcurrent protective device. Conductor insulation types, such as THHN, THWN, THW2, and XHHW, have different temperature ratings and suitability for wet or dry locations. The appropriate insulation type must be selected based on the application and environmental conditions. Conduit fill calculations are essential for ensuring that the conduit is not overloaded with conductors. The NEC provides detailed tables and examples for calculating conduit fill based on the conductor size and type of conduit. Cable trays must be supported and secured in accordance with NEC 392.30, which specifies the maximum spacing between supports and the methods for securing cables to the tray. Cable splices and terminations must be made in accordance with NEC 110.14, which requires that connections be made with approved methods and materials and that they be properly insulated. Overcurrent protection devices, such as circuit breakers and fuses, must be selected and installed in accordance with NEC 240, which provides requirements for the protection of conductors and equipment against overcurrent. Ground fault circuit interrupters (GFCI) are required in certain locations to protect against electrical shock, as specified in NEC 210.8. Arc fault circuit interrupters are required in dwelling units to protect against arc faults, as specified in NEC 210.12. Surge protective devices (SPD) may be used to protect sensitive electronic equipment from voltage surges, as recommended in NEC 230.8. Energy efficiency is an important consideration in electrical system design. The NEC includes requirements for energy-efficient lighting, motor controls, and other energy-consuming devices. Electrical drawings and documentation are essential for the proper installation, operation, and maintenance of electrical systems. Accurate and up-to-date drawings should be maintained and readily available. Proper training and certification are essential for electricians and other electrical workers. The NEC recommends that electrical work be performed by qualified individuals who have completed appropriate training programs. Regular inspections and testing are essential for ensuring the ongoing safety and reliability of electrical systems. Inspections should be performed by qualified individuals and testing should be conducted using appropriate equipment and procedures. The information provided is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer before designing or installing electrical systems. Electrical safety is paramount. Always follow safe work practices and use appropriate personal protective equipment when working with electricity. The installation of cable tray cable and metallic conduit for 3-phase, 4-wire, 277/480 volt system is a critical aspect of electrical engineering that requires adherence to strict guidelines and safety standards. It involves careful planning, selection of appropriate materials, and precise execution to ensure a safe, reliable, and code-compliant installation. The primary guiding document for electrical installations in the United States is the National Electrical Code. This comprehensive set of standards outlines the requirements for various aspects of electrical systems, including cable trays, conduits, conductors, grounding, and overcurrent protection. Compliance with the NEC is not only a matter of legal obligation but also a fundamental principle of electrical safety. Local building codes may also impose additional requirements or more stringent standards than the NEC. It is essential to consult with local authorities and obtain the necessary permits before commencing any electrical work. Manufacturers' specifications for the cables, conduits, and other components used in the installation provide valuable information on the proper application, limitations, and installation procedures. Following these specifications is crucial for ensuring that the equipment performs as intended and that the warranty is not voided. The selection of conduit material depends on the environmental conditions and the specific requirements of the installation. Polyvinyl chloride conduit is often used in corrosive environments due to its resistance to chemical attack. Galvanized steel conduit is a common choice for general-purpose applications due to its strength and durability. The size of the conduit must be sufficient to accommodate the number and size of conductors being installed. Overfilling the conduit can lead to overheating and damage to the conductors. Cable selection must be based on the voltage, current, and environmental conditions of the application. The cable must be rated for the maximum voltage that it will be subjected to, which in this case is 480 volts. The ampacity of the cable must be sufficient to carry the maximum current that the circuit will draw. The insulation of the cable must be suitable for the temperature and environmental conditions in which it will be installed. Copper conductors are generally preferred for their excellent conductivity and resistance to corrosion. Aluminum conductors may be used in some applications, but they require larger sizes to achieve the same ampacity as copper conductors. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which trips the overcurrent protection device and energizes the circuit. Bonding ensures that all metallic parts of the electrical system are at the same potential, which reduces the risk of electric shock. The NEC specifies the requirements for grounding and bonding in Article 250. Overcurrent protection devices, such as circuit breakers and fuses, protect the conductors and equipment from overloads and short circuits. The size of the overcurrent protection device must be matched to the ampacity of the conductors that it protects. The NEC specifies the requirements for overcurrent protection in Article 240. Proper labeling of electrical circuits and equipment is essential for safety and maintenance. All circuits and equipment should be clearly labeled with their voltage, amperage, and function. The NEC requires labeling in various sections, including 110.21 and 408.4. Testing and inspection are crucial steps in verifying the integrity and safety of the electrical installation. Insulation resistance testing, continuity testing, and ground fault testing should be performed to ensure that the system is functioning properly. A qualified electrical inspector should inspect the installation to ensure that it complies with the NEC and local building codes. Regular maintenance and inspections are essential for maintaining the safety and reliability of the electrical system. The system should be inspected periodically for any signs of damage or deterioration. Any problems should be corrected promptly to prevent electrical hazards. Electrical work should only be performed by qualified and licensed electricians. Working with electricity can be dangerous, and only trained professionals have the knowledge and skills to perform electrical work safely. The installation of cable tray cable in metallic conduit for a 3-phase, 4-wire, 277/480 volt system is a complex and critical task that requires strict adherence to safety guidelines, industry standards, and local regulations. It is essential to consult with qualified electrical engineers and licensed electricians to ensure that the installation is performed correctly and safely.